Hello, Miss Jody coming to you here with our first video for the Energy and Matter class that meets on Thursdays in the morning, 9:30 to noon. Obviously, we have been separated, and so now we're trying to get some of our work done while we can before too much time passes, and then hopefully we can get back together and finish some of our stuff actually together and not online. That is my hope. So during this time when we're separated, I thought what I would do is try to get some of the work done that could be done at home, and the stuff that's real important, our notes and our learning. And then when we come back together, we will be able to do a lot of our crafts and our science experiments that go along with the lessons that we've been learning at home. During this time, I'd like to continue to do the journals because we've got lots of stuff that we've done over the years and over this year in these journals, and I don't want to just not have the end of the year in them. So I was hoping to continue this same method, but obviously from home it's got to be a little different. So what I came up with is the idea of taking the notes with the video and putting them on a half sheet of paper like this. This is just a half sheet of computer paper that I just cut in half. And if you cut it directly in half, it's perfect because it fits right in the spot where the notes would be for the journal. So I will be keeping the labels so that we have the books all in order for our return, and then if you have your note sheet, it will be able to be glued right there on top of where the notes would have been if we would have been able to take them in class. So with that in mind, as you're taking your notes for the lessons, make sure you don't write on the back any notes, but on the back do write the title of the notes, like this particular one, chemical bonding. You would write that on the back because then when we go to glue them back in, when we return, we know which notes go with which page easily without having to read all of the notes on there. Okay, so if we do that, I think it's going to be good because what I could do is, like, say for instance for this lesson, I would do the note sheet and you'd be doing it at home, and say this was the craft I wanted us to do when we got back together. I would save that spot in the journal, and then when we'd get back together, I would just write a little note like this, chemistry, chemical bonding craft I wanted for the journal, and then we would do that one, and it would already have a spot ready for it in the journal saved, and we'd be able to glue it in. So that way we still have all of our opportunities for doing stuff that makes our journals exciting, but then also the experiments. So for some of the pictures, pages that we have, I'll still keep those because then when we come back we can do our experiments. And obviously this book, this journal is Benji's that I'm looking at right now, just because my journal doesn't have all of the notes and it doesn't have a lot of the pictures. Sometimes mine is lacking a little bit compared to you guys. So I thought I would just pull out one of those. But say I wanted an activity like this with Chernobyl when we were talking about nuclear fission and fusion and problems with nuclear energy. We would just save that spot and do it when we come back. Okay? All right, so with that in mind, also, you'll see I'm going to start using Benji's journal to show you the difference between the notes that you guys are used to taking and then the notes that I take in my journal, because I'm going to be using my journal, but I take a lot of notes. And so as we review where we're at right now, I'll show you the difference here, because I don't want you to get overwhelmed. And as we do these videos, I'm going to try to keep them one topic, one that goes together at least. Might be a label or two. It depends on how many labels go with that particular topic. You can slowly do the videos and pause it, and then you can write down whatever particular note, but you don't have to write every single word that I write, because I take a lot of notes. So say for instance this is Benji's notes on wave terminology, and then if you look at my notes on wave terminology, it might have a lot more, you see. And so I have little things on the side, and depending on how much time I have to put in my notes, if I do get time to put notes in my own particular journal, I tend to add a lot of extra things, and then when I write it up on the board for you, I try to make it a little more simpler. a little more simple. So, so that way we don't get overwhelmed or spend too much time on our notes. So you'll see with Benji's notes how we do a lot of the drawing, and you'll remember because we use a lot of drawings to help us understand these concepts. So I did want to let you know that when you look at my journal, I don't want you to get overwhelmed and think you have to write down every single thing. I want you to get the concepts, okay, the main things, and then draw out your pictures and use what you can for your memory tools. Okay, so let's review where we are in our energy and matter. We were a little bit behind on our syllabus, and that's because this book obviously is very intense and has lots of learning, and I'm trying to just scale it down. And those of you that are following along with the book, you'll remember that there's a lot of good information. I want you to do as much as you can and reading it and trying to absorb it, but it's hard stuff. And I don't know why I thought this book was like the other book similar to it that I'm using for Earth and Space Science. That's more written to a junior high level. Now, I know not all of you guys are in junior high, but I like to have books that are a little bit more challenging because I like to challenge you guys because you're so bright and you can do more than what just the average school kid can do. And so I like that about you, and I like that about our learning. So I do use harder books, but this one I didn't realize went all the way up to 12th grade. It was a 7th through 12th grade book. And so it has a lot of calculations and it's pretty in-depth. So it's okay if we don't get everything accomplished. We just want to get some of the concepts behind it, each chapter. So we are a little bit behind. So we're moving into, we started wave tech terminology, which is kind of understanding how waves, like what is a wave? And like, how does it work? Like, what are the characteristics that we can look for if something is going to be considered a wave? And then we're moving into sound, because sound is a wave. And once you understand the characteristics and the terminology with waves, then you say, oh, I see. This is why sound fits in this category. And then eventually moving on to electromagnetic waves so that we can understand those waves, because they're waves and they have a little bit extra going on. They're not just waves, we think they have a duality, a double side to them, and maybe they have the particles and such going on too, so they're kind of special. But there's a lot of wave things that we have to think through, and so we have to understand wave terminology. So looking at Benji's, and again, mine being a little bit with more stuff on it, and this will be easier because this one's already written. Now this one we have already done in our journals. So I'm going over this one just as a review of what we've already discussed, since it's been like 2 weeks. It's a long time, I want you to remember. But this one you don't have to do your own note page on. So just listen along with this as a memory. And then the next page I flip to will be your first one that you have to write out on your own half sheet. Okay, so when we're looking at waves, we first have to understand the terminology. Terminology means, how do I talk about waves? What words are going to be used so that I know when I hear these words, it means we're talking about waves. So first we have to understand, what is a wave? Okay, a wave is a periodic back and forth motion, and that motion we call oscillation. So whenever something's going back and forth, like boom, 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 it's the idea of a wave. So it could go back and forth like that, boom, 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 or it can go like this, up and down, up and down, up and down. And so we have different, two different main categories of waves. But basically, as the idea of a wave, it's that periodic back and forth motion. And we call that oscillation. That's the science word for it. And this oscillation can transmit energy. So as it's moving along, the energy is flowing along the wave. And so a wave many times will travel through what we call a medium. A medium is a substance that the wave can travel through. Now, waves like sound have to have a medium. They have to have something to like move through. They can't move through without something, because sound, and we'll see in our next video, sound is vibrations of the molecules and the atoms as it's moving through. So it's a disturbance that happens in the molecules, and they begin to shake, and then it hits the next one shakes, and the next one shakes, and the next one shakes. So it needs something to move through. But there are some waves, like the electromagnetic waves, that can move through nothingness, like empty space, no atoms, no molecules. They can just move through nothingness, and that's what we call a vacuum. And so we will see that later, that you don't always need a medium. There are some waves that won't need a medium. And so when we're looking at the wave world, this little drawing, if you can remember, we were talking about when the wave moves and it moves through the medium, and this was actually a water wave we were drawing. And so as the water wave is moving, we have a little boat on here. And I think in my drawing I have a little rubber ducky. The movement is moving up and down, but if you watch the boat, he's just kind of bobbing up and down. So he's not really having any net move. So he's not really moving like from one side to the other. And that's how it works with a wave who moves through a medium. And so imagine if this was sound, as sound was vibrating through and moving, boom, 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 and on. These particular molecules, it's not like they start over here and then they end up over here. They don't have a net move. A net move means like a total amount of movement. They just vibrated there and knocked into the guy next to him, vibrated, and then that energy went to the next guy, but this guy's still here. And so sometimes it's hard to visualize this with the waves, but as waves are moving through different media, we call in the plural, we're going to have different speeds. We're going to have different behaviors depending on what the wave moves through. But in the end, the wave, there's no net move on the medium. So it doesn't, like this guy doesn't jump and end up over here. He just did his little vibration and passed the energy on and passed the energy on and passed the energy on. So that's one thing about the wave world when it comes to mediums. Media. Then in the wave world, we also have the two types of waves. So we have the transverse and the longitudinal. So these are the categories of waves. So with these transverse waves, we were talking about this in good drawing on here, Benji. And excuse me if I sneeze here in a minute. I feel it coming on. And as I sneeze, I will send through the air a wave because the air will get moved by my energy flying out my nose. Pretty gross, right? But anyway, all right, so a transverse wave is a wave that's going to, and you've seen this before, it's kind of like the up and down. It's like the water waves. It's like if you take a rope and you start to shake it, and I don't have a rope right here, but say I've got my little pencil here. If it was flexible and I moved it up and down, it would start to like move like this, and you would see this whoop, whoop. And I will be attaching a video to this lesson that's showing some students doing some wave experiments to show that up and down movement. And with the waves, when you have a transverse wave, what's happening is the wave is being moved up and down. So picture this to be a string, and you're holding the end of a string or a jump rope, and you pull it up on one end, and then let's say somebody else is holding the jump rope or the string at the other end, so you pull it up and then you push it down. It will begin to make this wave along the string as the energy propagates, and that's what we use. That's a word we use in the wave world. Propagate means to move through, like to move the energy down. So as the wave propagates through the medium, which is the rope, then it goes up and down, up and down, up and down. And with transverse waves, they are always going to have this one particular property of the movement of the wave is going to be 90 degrees to the actual up and down movement of the actual energy source here. So when I move up and down this way, it'll make the wave move this way. So when it says 90 degrees, and you've seen this before in math, so it's talking like this 90 degree angle, like Benji had. And sorry, Benji, I'm putting this on here just to pull it out there so it can be seen. So this 90 degree angle, my energy's going up and down like this, my wave's going this way. Of course, it's going up and down, but it's going that direction. And so transverse waves are waves in which particles of the transmitting medium, so the medium itself, oscillate at right angles to the direction direction of the wave. And so there's always going to be that right angle side of things. Now, these are what we're going to see with transverse waves are going to be the waves we see when we come to the electromagnetic spectrum and we see light. They're going to be behaving in that way at that 90 degree. There's another category called longitudinal. And the longitudinal, and I usually try to have a slinky, and I didn't happen to have a slinky. And so I'm using this copper wire that I had from one of my classes, and I hate to bust this open because, see, they have this great little packet here so that you can get your wire out and never get it all tangled, and you can just keep it in this little packet and keep pulling it. It's brilliant. But, because once you get it out, then it's hard to kind of keep it orderly, but just so we see, I gotta bust this out here so you can see what this is, how the longitudinal wave, and one of my students busted one out a couple weeks ago in STEAM, and when we were building some electric circuits, and it was bouncing around like a longitudinal wave, and I was like, oh, perfect. If I don't have a slinky at some time, I can just always use something like this to explain it. But of course, I'm having a tad bit trouble cutting this guy out, or getting this guy out. Let me see if I can fold it. So if I am able to get this out to illustrate this to you, they've really sealed it in good so that it won't lose its coil, and I appreciate that, but not in a time when I want to try to use it, right? So let me see if I get a pair of scissors here. This might actually help me. I thought I should have opened it earlier. I thought that'd be real easy, but apparently not. Almost. There we go. I think I got it now. Yes. All right, so now I finally busted it out, and hopefully you got you know, some good memory going on with that there. But you see how I busted it out now, and it's starting to kind of be like the slinky idea. All right, so the longitudinal waves, they're always illustrated with this slinky idea because it's just helpful to see it. Because instead of going up and down, like the other one is going to go up and down, the transverse waves, it's going to be kind of like all about the coming together, the compressions, and then pulling apart. So when we start looking at these characteristics, we have what we call the compression, the squeeze side of the wave. So the energy is moving down the wave. And if I could somehow, whoop, there we go. I'm going to try to illustrate this here. Let me put this underneath my arm, okay? So I've got my longitudinal wave, and so if I put some energy into it, did you kind of see it kind of move down? It's kind of hard, but what will happen is, say this is the beginning of the energy here, the energy source, that I disrupt it. And so as I disrupt it, as it moves through, it'll make some squeezes, and then it'll bounce back up, squeezes, and that's how it moves down the medium. And so the squeezes are called compression. So a compression, and then when it spreads back out, to push, when it spreads back out, that energy pushes the next segment to squeeze. And then it pushes out and then squeezes the next one. When it pushes out, it's called a rarefaction. So you have the compression, rarefaction, and that rarefaction then bumps the next guy because he pushed out, and then that guy squeezes in, compression, rarefaction, and bumps that next guy, compression, refraction, and then eventually the wave moves all the way down the medium, and that's how it propagates. Where the other one was going up and down, up and down and up, this one's squeezing in and out, in and out, in and out, in and out, and the wave moves through the particular medium, like the copper wire here. And so you've seen that before with slinkies. That's why they're so impressive, is because they can make that squeeze and, woo, there we go. And you can see that particular wave side of things. So when we start looking at these two different types of waves, we have to figure out the side of what we call wave characteristics. Now this is where we stopped last time. And if you see, Benji started his notes, we ran out of time, but we'd already had the label, and we'd said, okay, the waves are going to exhibit 4 main characteristics, 4 things you can always look for in all waves. One is wavelength, how long the wave is. One is amplitude, one is frequency, and one is speed, or velocity if you need a direction added to it. So I said, write these 4 on, because we're going to look at the 4 so we know what they are and how they look in equations and all that. And then every time we study a wave, we would always write the 4 down, and figure out, how do we see this in sound? 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 Then when we move to electromagnetic spectrum, how do we see this in the spectrum? How do we see this in the spectrum? How do we see that? And so these four will be very consistent among all waves. So now I'm going to change to my page here to give you a little understanding, and I simplified this one from this page that I had on wave characteristics and wave calculations. So I kind of tried to make it a little bit more, here's more in notes, and then I tried to make it a little slimmer, okay, so that it wouldn't be too overwhelming. So this would be the first time that you would have to get your little half note sheet, and you'd have to start taking some notes. Now again, don't get overwhelmed, because as we talk about a topic, when I'm done explaining it, just hit pause, fill out what you need to for the note side of it, so you don't have to feel rushed like, whoa, slow down, Miss Jody, I gotta catch up, like we normally do, because our notes time goes, you know, chop, 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 and we're on it, and it gets a little, you have to keep up, where with the videos, you can kind of slow down. And the other thing I do want to note is for our little ones, when our little ones are taking notes, we don't require all of this crazy stuff for them, obviously. And what we do for them is just draw out some, we draw out a lot of different pictures. And so they might have one word, or say for something like this, what I would do for little ones is I'd put W, and then I'd put A, and I put F, and I put S. And then I would then eventually put the symbol of how it is going to be measured and shown in an equation, so they would get the correlation. But I wouldn't have them write out wavelength and all these notes and stuff, because what I do is I take my notes, and then when it's my time to work with the younger ones, I take these notes and just make them very easy for them, so that the concepts are still taught, but so they're not overwhelmed trying to write out all these words. Okay, most of our little ones are very good writers, and so we are blessed with that, and they're very good at paying attention, because we tend to have a more advanced type of student here at the Science Center, which is a blessing, because they can absorb more, and they are very excited about learning. But I don't want to overdo it and expect a little one to write all this out. So just so you know, I will next video grab a little video or a little journal from one of the younger ones, so you can see what that would look like. I don't want to overwhelm our little ones. All right, so, but finishing this one up, wave characteristics. So with the wave characteristics, like I say with Benji, we've got those four things, and we always have to memorize those four things, because that will be what we look at with all waves. So first thing is, what is wavelength? Okay, wavelength's pretty easy if you think about what the word's saying. It's wavelength. It's the length of the wave. It's how long is the wave. Some waves are really long, and some of them are going to be real short and small. And when they're really, really small versus really long is going to show us different things about their characteristics. So this is why we have to know the wavelength. Any two corresponding points on adjacent waves. So what that means is, if I draw a transverse wave, and it's going up and down and up and down. You see this little dotted thing I got going on here? That's what we call the axis. The axis is the flat line before the disturbance happened, before the wave started moving. So picture water as a transverse type wave. Okay, so the water's just completely still. And then you throw a rock in it. And then when you throw a rock in it, it begins to make all these waves going out of the rock, or where the rock hit, right? And they look like this, but they really look like this from the center moving out. But they're ripples, right? Because you threw a rock in there. And they will propagate out like this, these little ripples. So what we have to look at is, what would a wavelength be on a transverse wave? It would be any two corresponding points. So from a top to a top of a wave, or a bottom to a bottom of a wave. That would be a wavelength. The tops we call crests, so from crest to crest, or from trow to trow. And you would measure that. And so if it was a really long wavelength, that would be a long distance between these 2 points. If it's a short wavelength, then it would be a short distance. Like when we start looking at the electromagnetic spectrum and we start studying gamma rays are very, very, they have very short wavelengths. And so they're very, very small, and they're just boom, 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 like a whole bunch of them, compared to like a big, long wavelengths like the radio waves. So the radio waves will have these big, long wavelengths, and then the gamma rays will have the real shorter ones. And so you measure the wavelength from two of the points that are exactly the same, corresponding. So crest to crest, you don't go crest to trowel. That wouldn't be a full wavelength. That would only be a start of a wave and then halfway through a wave. It's got to go from the exact two same points. Okay, and so that's for transverse. But what about longitudinal? So when you are measuring a longitudinal wave, that's the slinky-like wave, we still need 2 points to work with, right? So I told you compression, that's when it squeezes, and rarefaction is when it spreads out. So what we need to do is the same thing we did here, the same point to the same point. We have one compression pulse to the next compression pulse. Then that would be one wavelength, not compression to rarefaction, not a squeeze to a spread out, but a squeeze to the next squeeze, and that would be one. And or a rarefaction, one rarefaction to the next. So one spreading out all the way to the next spreading out. So we would be able to measure that. And when we measure our wavelengths, we use a length measurement because that makes sense. When you're using length, you use length measurements. And if we are staying in the metric, we can measure these in the metric system with the base as the meter. But of course, if you were measuring really small wavelengths, you might measure in centimeters or millimeters. If it's really, really small, or even smaller than that. If it's really, really big, then we could do decameters or whatever. But the base would be meters. So it's going to be measured in meters. Now this, and I boxed all these in so we could see these. I circled all the 4 characteristics, and then underneath the characteristics, I'm trying to make it stand out, I boxed in the symbol you would see in a equation. And so the symbol is the lambda. So this symbol means wavelength. So if I write an equation, and I'll show you one here in a calculations page. So you see how I have written V is equal to wavelength times frequency. See my little wavelength? That means that I am representing the length of the wave. So I'd have to measure the wave, and I'd have to then stick that into that part of the equation. And so the lambda is how we would write out wavelength for our equations. All right, the next one, amplitude. Now, amplitude is another one of the 4 main characteristics. It's the maximum distance the particles are displaced by the wave. So what that means is as energy is flowing along this wave, because the waves are propagating through the medium, and energy is pushing its way through, because you started it here at the top where you shook it, or you dropped a rock in, or whatever you did to make the wave start happening. The energy keeps moving down and down and down. Now, when it comes to amplitude, it's not about how long these waves are, like the wavelength, it's about how high they go. So what a wavelength would be is, I remember that imaginary axis right here, the water before it got disturbed by the rock, and it was perfectly flat. We would measure the amplitude from the point of where it would have been still up to the point where now it rises, or vice versa, how far it goes down under. So your wavelength, your amplitude is just how high does it go up here. So not the full movement of the up and down, only from the axis point up. So when it was still, how high did it go up now? That would be your amplitude. So if I drew this wave out right here, I have like a low amplitude. But see, as I get farther down, I've got this high amplitude. I just drew that to symbolize that we could have different levels of amplitude. So this one would be a lot higher. So I would say this one has more energy. If it doesn't move that much, a little ripple, boom, 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 and it doesn't come up that much higher than the axis point, then it doesn't have as much energy. But if it really flies up there, and so just imagine instead of throwing a rock in, you do a cannonball into the deep end, and then that's a lot more energy going into the water than your rock was. And so your waves are going to be a lot higher. They're going to have more amplitude because you are definitely adding more energy to that situation. So amplitude directly relates to the energy of the wave. And so you're going to measure just that top part, how high it raises above the time when it was still, which we would call the axis. Amplitude is going to be measured in the big A. So we have the big A for amplitude, and I think that's right, big A. You know, sometimes my letters get mixed up, and I'm like thinking, little a, what's little a? Because see, in physics, you have to keep track. Sometimes they're using big A for something, and then in the end, you have a little a, and you think, well, maybe that means the same thing, and it doesn't always. But I'm pretty sure amplitude, I'll check that. But in amplitude with big A, and then we can, that's what we would use for our equation. So if I needed to put amplitude in the equation, I'd put a big A, or to figure out my amplitude, and this would be measured in meters. Same like this, because it's a length. It's how long this is between these two. So this one's how long it is this way, but this one's how long it is this way from the axis up. So we'd be measuring the same way. We would have either meters, centimeters, millimeters, or if it's bigger, going up above the meter part into decameters and on. Okay, and then the next one is frequency. So frequency is going to be the number of waves, crest or trough, that pass a given point per unit of time. So what this is all about, the frequency, if you heard it before, oh, I got to tune my radio into a certain frequency. That's what we're talking about here. Frequency is as the wave is moving, we have a certain, let's say we have a certain area of time. Like let me put my pencil here, and I say, okay, in 1 second, how many times does the wave hit me and go past this one point, okay? So I'm gonna be the pencil, and then for 1 second, let's pretend, the wave is just like up and down, hit once, the next one, next one, because it keeps flying past me, right? And so that would be maybe a certain frequency, maybe hit me 5 times, okay, during that point of time. And so I would say, boy, how frequent is that wave hitting me? That would be my reference point, right? And so if I had a really low energized wave and it was really long, and along came the wave, and he only hit me once in this time, let me pretend to do this with my hand. Here's a big long wave. Boom. He only hit me once as he was traveling along. Then he would have a low frequency. But what if I had a really, really highly energized wave, and it was like so up and down I can't even do it with my fingers? Let me just try to do it with pretend like my little pinky finger is the wave, and he's going up and down, up and down, up and down, up and down. And as he's flying past me, it keeps hitting me, because so many little waves are going past in a certain amount of time. Then I'd be, wow, that has a high frequency. It's really a lot hitting over that certain amount of time. So frequency is the number of waves that pass a given point per unit of time. So I tried to draw this out and say, okay, in this amount of time, like a 1 second time frame, it maybe hit this point. If this kept moving, it would hit 1, 2, 3. Maybe if I did a little farther, it'd be like 4. But let's just say at least 3 times it hit that point, or past that point. Then I would say, oh, that's its frequency. And so frequency is really equal to the waves, how many waves you got going, divided by the amount of time you gave it. And so if I only gave it 1 second, I would say this guy, it hit me like 4 times in 1 second. So this would be, the waves would be the number of waves, N. So 4 waves hit me, and the time would be 1 second. In 1 second, 4 waves hit me. And that's how I would measure the frequency of a wave. And so different waves have all different types of frequencies. And the ones that have a little lower energy, there a lot of times, especially when you talk about the electromagnetic waves, the ones with lower frequencies aren't going to be as dangerous. So if you're in, say, in the presence of something like a radio wave is a transverse wave like this, but they're really big and they're really long and they're not very frequently hitting you. And so they're not going to be doing any damage to your body. Like if you're in the presence of a gamma ray, which is very high frequency, a whole bunch of them, and very small wavelengths. And so they would just, hit your body like about a quadrillion times. A quadrillion waves would hit you in 1 second. Well, when those waves are hitting you, especially in the gamma wave, that's filled with a lot of energy, and your cells can't handle that much energy hitting you all at once. That's why we talk about things like, ooh, you don't want to be around a gamma ray, or you don't want to be around X-rays, because they're also high frequency and they'd be hitting your cells lots and lots of energy flying at your cells in 1 second time. So instead of being like, oh, this hit me three times in 1 second, I would be like, oh, the gamma ray hit me 14 billion times in 1 second. And that's not a good, that's not quantitative data. That's not good numbers. I'm just making that up. But you see what I'm saying? And so frequency will help us understand how waves, whether they're okay for us to be in the presence of, especially in the electromagnetic spectrum, and whether that's not a good idea for us to be in the presence of some of those really high frequency waves. Now, frequency is the little letter F here. And so that's the symbol I'm going to use in my equations. And you saw it when I was showing you the wavelength, the lambda one. You see it in this wave calculation here. I've got V is equal to wavelength times little f, frequency. So I can figure out a few things in my wave world, doing wave calculations, which we'll talk about later in another time. But that's going to be my little guy. So you see it, frequency is equal to waves over time, and n can be the number of waves, and t can be the amount of time that passed. And this is going to be measured in hertz. Now remember, these guys were measured in meters because it was a distance, and this was a distance. Now hertz is going to be a measurement that's going to help us with understanding frequency. And that's going to be how many waves per second. So I have 1/s, which means 1 wave per second, and I would change this obviously to the real number of how many waves were hitting me. But this would be my measurement, and when we do that, we call it the hertz. When we do how many waves per second. And that's after Heinrich Rudolf Hertz, who was famous for understanding how and creating a tool to be able to create these electromagnetic waves, radio waves in specific, and to be able to transmit them. So that's why we have wonderful, the energy transmission we have now with all of our radios and cell phones and all that stuff. That all works on the principle that Heinrich Rudolf Hertz figured out for us. Well, he wasn't the only guy. Lots of men along with him figured out those things, but he built that particular original device. All right, then we have the last one, speed. So speed, obviously we're familiar with speed because we already studied speed and velocity when we started in our physics, but speed is the rate at which the wave travels. So how fast is he traveling? Now we know that we can use the word speed when we don't need any direction. So someone might say, oh, what's the speed of light? Well, if you're just saying how fast is light going, you're not saying, oh, did light get from here to there? Did I turn on the flashlight over here and then it went that direction? If I'm just saying the speed of light, I don't need any direction, so I can call it the speed of light, because I'm just saying that it's just the rate at which it's traveling. I'm not adding the direction. But if I add direction, we know that it becomes a vector. If you remember from our studies at the beginning of our physics unit. Vector means I'm adding direction. It's a vector quantity. And so velocity has to be used if you're going to add a direction. And so you can see on my wave calculation over here that I showed you before when I was starting to calculate the speed, it had to be changed to velocity. You see that there? Because there was going to actually be a certain direction to this wavelength. So instead of doing a little s, I have to change it to v for velocity. So you can see here we've got s for speed, and we know the formula for speed because we studied already. Speed is equal to distance over time. And then when it comes to changing it to velocity, the vector, because we got to add direction, it would be v is equal to distance over time. So they're the same thing. This one's just saying that it's going to have some direction. And this is going to be measured in 2 units. Now the reason it's measured in 2 units is you're saying how far did I go over a certain amount of time. So if you're using 2 things and you're figuring something out, you can't just pick one. Well, I'm only going to use seconds. Well, then how will I know how far you went? Because I wanted to know how far you're going in a certain time. Okay, well then I'll just use meters, and I won't use seconds. Well, how will I know how long it took you to get there? So some units are going to need to have 2 things or more to them. And so this is going to be measured in meters per second. And so when I'm doing my speed or my velocity, I say she was traveling 32 meters per second. You've also heard something like that with the English version when we say, oh, I'm driving in the car 60 miles per hour. That's just another version of this distance and time unit, but it's using the units of the English, the miles. And then of course, seconds, hours, minutes, they are used on both units, the English and the metric system. So those never really change. But you can change that depending on what you don't want to have to say, I drove to Florida this many meters per second. Well, we don't really need to know that would be a big number. We can just do it in hours. Let's do it in hours. Like it took me this many hours to drive this many meters, right? Or I could change it to miles per hour. It would just be depending on what you're trying to solve. Okay, so that pretty much ends our topic here, which is on wave characteristics. And though I started on wave terminology, that was just to remind you. And so finish this page, and again, don't forget to do it on a half sheet. Don't write on the back unless you just write the title of the note sheet on the back, but don't write your notes. If you need 2 pages, say you write really big and you need 2 pages, that's okay. You can do 2 pages, and then I would just glue them right next to each other. Okay, so don't, or if I end up keeping the journals all in order and you had 2 pages, I would glue it like this and then glue one underneath it. And so you would be fine. Okay, so that way we'd have all your particular notes that you did at home. But again, don't get overwhelmed with having to write everything that I've written. And then also little ones, definitely don't try to write all this stuff out. You can just do as much as you can, or you can watch some of the videos. You don't have to be overwhelmed with every single detail. This is obviously more for the older students, and you can pare it down. And your parents can help you also too. And if you get overwhelmed at all, you can just contact me and I can talk you through a couple things too. Okay. All right. So along with this video, I will be posting the some other videos for you to watch. I'll give you some visuals of this area of wave characteristics. And then when we get back together, we'll do some experiments of understanding how waves work. Okay, talk to you later.